some of you all probably have, I don't know, varying amounts of experience with inequalities, but I want to, start out with some pretty, basic results to be, to be sure that everyone is, knowing some good stuff. Okay, so let's start with, the most foundational inequality of all, even more than the Amgm inequality, the trivial inequality. For all real numbers x squared is at least 0. Indeed, it's really quite trivial. It's just, if x is positive, x squared is positive. If x is negative, x squared is positive. If x is 0, x squared is 0. So, on itself, this is like nothing, but when you combine it with a bunch of other stuff, you can really build up a lot of other stuff from this. So then, let's move on to not so trivial things. So the next thing is Amgm. And I want to look at it this way. If you have some non-negative real numbers, a1 through an, and suppose you have fixed their sum. Say it's S. And you want to maximize their product. And, feel free, is there, is there a chat feature on? Oh, okay, there is a chat feature. Oh yeah, you can feel free to, put, if you have questions, feel free to, put them in the chat or comment, or if I'm going too easy, if it's too easy, if it's too hard, feel free to put comments in the chat whenever. So yeah, so say you have some real numbers, a1 through an, and you fix their sum, and you want to maximize their product. So, maybe a reasonable, if you play around with some examples, you could see that moving numbers closer together sort of seems to increase their product, and moving them farther apart sort of seems to decrease their product. So you might want to conjecture that the maximum is achieved when all the numbers are equal. And well, I'll say S over N equals M, the mean, the arithmetic mean of the numbers. So, we want to prove that the maximum is M to the N, which is achieved when they're all equal. So we want to prove that their product is at most M to the N. And so this is basically the Amgm inequality. Normally you would write it as, with nth roots, but this is what's going on. You would write it like this. And this is useful in all sorts of inequality problems, but let's take a minute or two to focus on what's really underlying this. So you have this. So let's prove this. Now there are a lot of ways. There's more than one way of proving this. There are quite a few ways of proving this. And so one way, so you might have seen some proof of this before that has like some weird way of doing it where you like induct on powers of 2 and then you go backward to induct down to cover all the gaps in between. Some weird complicated proof, but there's no need to do that. We can just prove this by straight up induction. So base case, I guess, n equals 1 is trivial. Or not even trivial, it's just like clear when n equals 1. So now let's do the inductive step. So what we're going to do is sort of this nice idea that shows up in various inequality problems where you sort of can move the variables around to improve what you're trying to show. So what we're going to do is, among the AN, we're going to take the largest one and take the smallest one and move them closer together without changing their sum. So, okay, let's say A1, assume without, since it's all symmetric, we can make some assumptions. So assume without loss of generality that A1 is the largest and AN is the smallest among the AIs. Or at least, tied for largest, tied for smallest, whatever. You could just say, assume without loss of generality that A1 greater than or equal to A2 greater than or equal to A3 all the way to AN. We only need the largest and smallest. So let's assume that. Now, let's take a look at if we replace A1 and AN with, so we want to replace them with two numbers with the same sum as they originally had. And if we want to make it easier for the induction, you can just, it would be nice to replace one of them with M. So let's look, A1 times AN. Let's think about replacing them with M and A1 plus AN minus M. Now notice, this minus this is A1 times M times AN minus M. So since A1 is since A1 is less than or equal to all the AIs, A1 minus their mean is less than or equal to 0. Similarly, A1 minus their mean is greater than or equal to 0. AN minus their mean is less than or equal to 0. So this product is less than or equal to 0. Great. So we can say this, meaning we can multiply by all.
You're muted. Yes.
Hey, Luke, I think you got muted somehow. That shouldn't be possible. Can you check?
Oh, I'm unmuted now. Could people hear what I was saying that time?
For the past few seconds you were muted.
Oh, but have you mostly been able to hear me?
Yeah.
Oh, someone said in the chat, anyone can mute him. Yeah, I kind of forgot how Google Meet is. I think people by default have some amount, maybe people, I remember there was some comedy skit some friends of mine did once involving having the power to arbitrarily, well, you can do some things in Google Meet. So yeah, I guess just please
Yeah,
don't
fix
mute me.
that. No, fix that. Can't happen
Oh,
now.
okay, thanks. So yeah, okay, I guess we'll just say, so we have this A1 times AN less than or equal to M times, A1 plus AN minus M. So basically we take the largest and the smallest and we move them somewhat closer together. And now this will let us induct down. Because, now look at this, we have n minus 1 real numbers. And what is their sum? Their sum is the sum of all the AIs, which is S, minus M, which is equal to n minus 1 times M, meaning their mean is M. Meaning, by the inductive hypothesis, their product is at most M to the M minus 1. And so we're just done. So basically, what you can think of this as happening is like when you have a bunch of non-negative real numbers. I guess I should have noted that here. When you have a bunch of non-negative real numbers, and you want to maximize, if you fix their sum, then maximizing their product means making them all equal, because informally you can think of it as just moving them closer together increases the product. And so you just sort of move them one by one to the mean. And you just repeat it. If you repeatedly do that in the right way, you just get what you want immediately. And so should I go over any part of that again? Any questions about that, or should I move on?
No doubts.
You can move on.
Okay. So moving on, yeah, you have the Amgm inequality. And so there's another way of looking at this that relates to another notable inequality. So okay, you have this. And so there's another way of looking at this that relates to another notable inequality. Which is like, if you take logarithms on both sides, you can think of this as saying logarithm a1 plus ... plus logarithm of an. And now I guess I'm assuming they're all positive. If any of them is 0, this is just trivial. So we're assuming, and you get this. And so this is sort of a special case of Jensen's inequality, which is Jensen's inequality. I don't, maybe I won't go into too much detail, but basically it talks about when a function is convex or concave. So it's sort of a generalization of this. Like with logarithm, you have the graph looks like this. And so sort of it's concave. I don't know exactly what the terminology I'm supposed to use is, but like this is a concave function, meaning one way you can think of it is like its second derivative is non-positive. And similarly, in fact, in this case, you can even say the second derivative of logarithm is negative, actually. And so you get something like this. And so, in fact, there's a version of this, of Amgm, where basically we've weighted. So the point is like replacing some points on a curve with the weighted average, if it's concave, sort of will increase you want to move them closer together on the concave curve. I don't want to go into too much about Jensen, but the point is, there's also a version of Amgm where instead of just having 1 over n, you can think of this as like a factor of 1 over n. Instead, if we have weights, if you have just some non-negative real numbers, w1 through wn, you could get this, that sum to 1. You could get this. And if the w, and so raising back to a power, you would get weighted Amgm, which showed up. So if w, it's like, let's see, the ai's and the wi's are non-negative reals, or no, I will say, let's say, oh, the ai's are positive reals, the wi are non-negative reals, and then that sum to 1. So then you have that the product of AI to the WI is less than or equal to the sum of WI AI. And like if the W's are all rational numbers, this is basically just equivalent to normal, usual AMGM, just with, you know, varying amounts of stuff. Like on two variables, if I wanted to say like x to the 1/3 times y to the 2/3 is less than or equal to 1/3 x times 2/3 y, you can just sort of think of this as like the geometric mean of x, y, y is less than or equal to the arithmetic mean. And so, but yeah, you can think of this as sort of a generalization of AMGM, which is usually you don't really care too much about this if you can just get what you want with standard AMGM, but it can be a useful trick. Also, this can help you sometimes if you have a problem where there are variables in the exponents. It can help you handle that sort of thing. There was a particularly notable example of a problem with variables on the in the exponents recently. That was, you know, some of you may know what I'm talking about. It was on the IMO in 2020. I may cover that as an example later. So yeah, that's a problem where weighted AMGM was very useful indeed. Okay. So, but let's see. So it's not all about just maximizing the sums and products and whatnot. There's a more general thing where you have. Oh, well, wait. Actually, before I move on, I should talk about the equality case of AMGM, which is, you know, you could check in the proof that we did that in fact for equality to hold in regular AMGM, all the AIs must be equal. I feel like there's a similar thing you can say about weighted AMGM, but I'm not 100% sure. So yeah, that's the equality case. It's pretty obvious. But yeah, so this is another good thing to know. Okay, but let's move on. There are more general versions of AMGM, like the so-called power mean inequality, where instead of just, you know, you can think of it as like A1 to the lambda plus, you know, hang on, I think my cat wants to play with the wires of the computer, and I don't. Yeah, anyway, okay. So, you know, for lambda equals 1, this is just the usual old arithmetic mean. As lambda approaches 0, I think this is supposed to give you the geometric mean, but you could do other things like square everything, take the arithmetic mean, and then square root. And so you have this power mean inequality that tells you that this is an increasing function in lambda. So sometimes this is useful, especially in special cases like for this, like this, the square root of the mean of the sum of the squares is at least the mean of the numbers. Or you might also care about the harmonic mean, which is the reciprocal of the mean of these. So sometimes you care about this, but you know, not the most frequent thing. Oh, yes?
Does the weighted version, like weighted AMGM, hold if the weights don't sum to 1?
Well, I think in that case, like the thing that's happening here is that sort of if you think of this as like you would want, since this is a linear function of the AIs, and so sort of you want this to have degree 1 in the AIs as well. So you want sort of the total degree to be 1. So you want the WIs to sum to 1. If they didn't, you know, like you could I guess make, if you really, if you really want general WIs, I guess you could, divide out by their sum before you raise it to exponents, and then just, deal with that. But this version of weighted AMGM, you need them to add to 1. For this sort of reason of like homogeneous. Like otherwise you would, if you just plugged in 1 and 1, you would get something like xy less than or equal to x plus y, and it's like you can see that this will like not work if you just sort of take x and y really big. This is sort of quadratic, and this is sort of linear if they sort of get big at the same rate. And so, but you could have a version like this. So yeah, so that, I hope that answers your question. Oh, I see some people are talking about IMO 2012 number 2. No, the one I was talking about is IMO 2020 number 2, but I might talk about IMO 2012 number 2 later. I guess we can talk about IMO 2020 problem 2 now if people want. Okay, sure. Let's do it now.
So by the way, what was the proof of that? Like you mentioned, a1 ki power lambda plus a2 ki power lambda, so until an ki power lambda, that thing. What was the intended proof?
To be honest, I think you could. I think you might be able to. I guess you could probably prove it using like Holder's inequality, which I plan to get to later, but you could probably actually do it with some clever, like, I guess you could probably do it with some clever AMGM, something like, if you scale it right, like say you wanted to prove like the cube root of the sum of the cubes, the cube root of the average of the cubes is greater than or equal to the square root of the average of the squares, say. Well then, since this is homogeneous, we can sort of scale all the AIs. So we can sort of say, assume without loss of generality, like if it's all 0, it's just clear. So, okay, assume without loss of generality that the sum of the AIs cubed is n, and then we want the sum of their squares less than or equal to n. But now you can just sort of do this term by term, where you sort of get a1 squared as sort of a weighted geometric mean of a1 cubed and 1.
The sum of to be n squared. Oh, okay, never mind.
Oops. You can just get something like this, and then if you just add it up over all the AIs, you get what you want. This is a thing that can be useful sometimes, where you like get an inequality for each individual variable and then you combine them somehow. And then you could imagine generalizing this. But it would be more natural to use Holder's inequality, I think, which I plan to get to later. But the proof of Holder's inequality is something kind of like this. But yeah, I should talk
How
about
exactly
that
to use Holders here?
later. I mean, okay, I can. I'll get to that later once I've talked more about Holder and Koshi Schwarz, but I'll definitely mention that later. So yeah, but for the moment, if people really want to see an example of weighted AMGM and also want to sort of kill a problem from the IMO, let's have a look. Let's have a look at IMO 2020 problem 2. This is maybe an instructive problem in some ways for what you can do with inequalities, but also this is just not a very good problem. It's like a lot of the algebra problem, maybe like, I kind of wish this problem had not been on the IMO, but it was on the IMO, so we can do it. Okay, so the problem is, let me get the exact statement. Basically, you have some numbers A, B, C, and D, where A is at least B, is at least C, is at least D, is greater than 0, and they sum to 1. Prove A to the A times B to the B times C to the C times D to the D times A plus 2B plus 3C plus 4D is less than 1. So I'll give you all a few minutes to think about this. Maybe like take a few minutes and think about this. But yeah, and then I can tell you what to do. And maybe a lot of times I don't really want to spoil problems too much without giving you enough time. But in this case, like, this problem is just not very good. It would have been better if it were not on the IMO. So I don't feel, it's not as bad for me to spoil it.
Wait, why shouldn't it have been on the IMO?
Because, well, part of it is that it's an ugly statement, but also part of it is that the solution is sort of bad and ugly in a certain specific way. It would, I can explain more after. It would be a bit of a spoiler for me to say now why, but the solution is not very nice. The solution is not very nice, and the statement is not very nice either.
Do you mean it's complicated? Like, sort of?
Well, like, not just that it's complicated, but like, it's just sort of like, it's sort of contrived in sort of an ugly way. Like, it's just this random algebraic expression, like, you have no reason to ever care about it. Whereas, like, you have to give you an example of another problem from the IMO 2021 problem 2 is also an inequality, but this one is a much nicer problem, which is just for real numbers x1 through xn, prove that the sum over all I and j from 1 to n of the square root of the absolute value of xi minus xj is less than or equal to this. I don't plan to discuss this problem today because it's actually quite difficult. But
actually, some part of your right code is not visible.
Is it? Is it? Should I? Is that
Yeah, now, fine.
okay? Yeah, like for this problem, like at least it maybe looks a little bit nice. And also it turns out that the solution to this problem is pretty nice. So this is sort of an example of a better problem that was on the IMO. So for this problem, it definitely deserves to be on the IMO, whereas this one is just sort of like a random mashup, whereas this one you can sort of see like, oh, it's, you know, it's a neat way of putting things together. The one on the right is more interesting, I would say. But anyway, yeah, you can take a couple more minutes to think about this one, and then I can tell you the proof, which is not the nicest proof, which is part of the reason people didn't like it being on the IMO. I'll give you all like 2 more minutes to think about it, and then I can tell you what's going on with it.
Does taking logarithms help here?
Not really. I'll say that weighted AMGM is definitely involved.
Basically, with weighted Amgm inequality, will get a plus 2b plus 3c plus 4d into a to the power b to the power c to the power c d to the power d is less than or equal to the this a plus 2b plus 3c plus 4d into a square plus b square plus c square plus d square, and then we can overkill the problem.
Yes, okay. This is indeed, you want to apply weighted AMGM on A, B, and C and D to get A to the A plus times B to the B times C to this different marker. That this is, since they sum to 1, you can get that it's less than or equal to A to this. Yeah, and so it turns out that like this is actually like sufficient. Like you can actually, that this will actually give you a solution, because now if we want to prove this, is less than 1. Well, 1, now this is, at this point, like we've reduced it to just like a polynomial inequality. So if you homogenize, saying that what, since this is a cubic thing on the left-hand side, like has degree 3, you want this to have degree 3, so it's nicer to write it as a plus b plus c plus d cubed. And now, like, there are ways to finish where you just sort of do some computations. Like, if you just expand both sides, you can get that, like, you can just cancel some terms and just pair up the remaining terms in a certain way, and you just do the bash, and it just works. But that's a lot of computations. And it's you know, part of the reason why this problem is not so popular, because like you do a lot of like, why should there be so much computation? Another way you can finish from here more systematically is like, you can plug in new variables for the differences. Like if we want to reparameterize them as like A equal, like D equals U, C equals T plus U, B equals S plus T plus U, A equals R plus S plus T plus U. Then we know that R and S are non-negative and U is positive. And then you can just plug them into this and expand it and hope that you get something where like coefficients do what you want them to. And indeed, you can actually solve the problem this way. This is actually how I solved the problem on the IMO. It was not the most pleasant experience, but like if you actually just plug this in and, you know, subtract the left from the right, you get something where all the coefficients are non-negative and the coefficient of U cubed is positive. And so you just win. If you really like computation or something, you can do this as an exercise. I don't want to do the computation right now. It's not enlightening. But yeah, and if you want to see the way that where you just pair up terms, it's on Evan Chen's website. You can, in his notes for the solutions to the IMO. So if you're curious how that works, you can take a look. But yeah, I think there's another way of doing this where you just say like, this is the official solution does something like, this is at most a cubed plus, I mean a squared plus b squared plus c squared plus d squared times this, and then like replace it with a squared times this plus b squared times each symmetric thing, and then you get something that's just the same as what you get when you expand a plus b plus c plus d cubed with some terms left out, and it's positive. But this is also not the nicest thing. And so this is sort of part of the reason why this problem is maybe not so popular, in that it, like for an IMO problem, somehow people do not expect the solution to just sort of be apply weighted AMGM in the most straightforward way and then just sort of hit the problem with a hammer until it dies. So maybe like some contestants figured, oh, like thought of this weighted AMGM, but then decided to themselves, oh, it can't be that easy. This is an IMO problem too. And then they sort of psych themselves out. And then they just were trying to do more complicated things with exponents and weird stuff, when actually it's just this simple thing. I think there is at least one other way you can do it, but you know, and so that's sort of part of the reason why this is unpopular. And even though the solution is simple, this problem is not so easy. In fact, no country had all 6 team members solve this problem. Not the US, not China, nowhere. And so this is not such an easy problem, but yeah. But yeah, let's move on to nicer things. If you're curious about the other solution I mentioned, you can see in the stuff about problem 2 here. But this is not a nice problem, so let's move on to nicer things. Oh, and just one other thing, in the inequality you get from this, like you really want you really need to use something where they're actually positive, to actually get that it's a strict inequality, because like this is why I said, oh, the coefficient of u cubed is positive, because we know u is positive, and so we want it to be strict. Because like if it was only non-negative, this would sort of approach a non-strict inequality. If A approaches 1 and B, C, and D all approach 0, then the whole thing just approaches 1. And so you can sort of think of that as like an equality case in the limit. Not really, because 0 to the 0 is undefined, but it would sort of approach 1. And so that's why you sort of want to be careful to be sure to prove that it's sharp. Or, sorry, not sharp, strict. That it's strictly less than 1. So it was necessary to take some care with that in some solutions.
By the way, do you know what was the rubrics of this problem? Like why 3 marks were awarded? A student from China got 3 marks.
Okay, I do know about the rubric for this problem. So a lot of students got if you proved a to the a, or like if you reduce to the, if you proved this, and like you had to actually cite, like you could say like by weighted AMGM this, so it's sufficient to prove, you know, the thing you get by plugging it in, but then you didn't prove the polynomial inequality at all, you would get 2 points. A lot of people got 2 points this way. Like if you were to look at the statistics. There were various other ways you could get points, but like you see, the number of people who got a 2 on this problem is almost as much as the number of people who got a 7. There were a lot of ways you could get points on this problem. So that was the rubric for how you would have the most standard solution. But there were other items on the rubric where I don't know exactly what the student from China did. If you prove, actually, you would get 3 points if you proved just the polynomial inequality without doing the AMGM part, but I kind of doubt that's what happened. There were also some other way where you could get partial, like if you prove the problem for the case of A being greater than or equal to 1/2, which you could, you know, do in a number of ways, you would get 4 points. I guess you could do it in a number of ways. Like you could get 4 points. And so perhaps the student from China got partial credit for like progress toward doing this, like being almost complete or something. I know that was a way that some partial was given. So maybe the student from China did it that way. But yeah, like often in coordination at the IMO, sometimes like the idea is like students submit their scratch paper, and then like your country's leader can try to sort of argue based on what you were doing in the scratch paper, like, oh, the student could have come up with this solution or something if all they needed to think of was this, you know, something. And then like, and so part of coordination at the IMO involves like thinking about, like the leader can try to sort of think of like how to finish what you were doing in your proof to get to a proof, the leader or, you know, other people. And so, you know, presumably they might have had some coordination work where you try to finish what you were doing and then talk to the coordinators, the, you know, the sort of impartial judges who will take a look and see whether you're making a reasonable argument or not. And so there were probably, you know, various ways someone could have gotten 3 points on this problem.
Okay.
And also there were ways you could lose points. Like, for example, if you had a completely correct solution, except you didn't prove you didn't handle why the inequality is strict at all, you would lose a point. And you could lose points in other ways for being careless in various ways, missing parts of something. Like, you know, you'll notice that the American scores on this problem are 4 7s, a 5, and a 3. The 3 was something the 3 was sort of, anyway, I don't want to, not to go into too much detail, but you can imagine perhaps what happened. But yeah, no country had all 6 of their students solving this problem. So yeah, anyway, let's move on to nicer problems. Koshi, or nicer things, Koshi-Schwarz. So the Koshi-Schwarz inequality. So this states that if you have 2 lists of real numbers like this, and so there are a few different ways you could prove this. So if you're wondering, like intuitively, where does this come from? Well, let's look at 2 vectors in n-dimensional space where you have a1 through an and b1 through bn. Let's call it v and w in n-dimensional space. Well, this is just the length of v squared. This is the length of w squared. And then over here, this is the dot product of v and w squared. Now, this dot is actual multiplication, whereas this dot is the dot product. And now you may know that in our regular 2-dimensional world, the length of the dot product, or no, actually just the dot product of 2 vectors. Yeah, the dot product of 2 vectors is the product of their magnitudes times the cosine of the angle they make. And so if you plug that in over here, you just get like, I'll put this in quotation marks because this wouldn't really be a rigorous way unless we actually talk about why you can do this in n-dimensional space with the angle between 2 vectors. Why would this work? But sort of this can give you, like, if you look at what's happening, then this is just saying like the only way you could have equality is if one of them is 0, or if the cosine squared is 1, because the cosine is between 1 and -1. And so this sort of gives you a hint as to what the equality case is when the vectors point in this, when they're all 0, or when the vectors point in the same direction, if you want the angle between them to be 0. And so to be more rigorous about it or something, how do I want to say this? So there are a couple of different proofs. One proof is actually you can just directly make this follow from the trivial inequality in that the left-hand side minus the right-hand side is just equal to a sum of squares. Namely, it is the sum of aibj minus biaj squared for I and j, like 1 less than or equal to I, less than j, less than or equal to n. You can just like check this by like expanding. It's not hard to see. And so this is just one way to just prove it. I think this identity actually has a name. It's like I don't remember. It's like Lagrange's. I don't remember exactly what it is for sure. Another way you could prove it is you could define a quadratic polynomial. F of t is the sum over t of the sum over I from 1 to n of ait minus bi squared. And now this sum of ai squares is the coefficient of the quadratic term, and basically the inequality boils down to saying that the discriminant of this quadrilateral of this quadratic polynomial is less than or equal to 0, which is true because this polynomial is always greater than or equal to 0. And so if it's always strictly greater than 0, the discriminant will be negative. If it's equal to 0, it can only be okay, I guess I should say, if the AI are all 0, it's trivial. Otherwise, if it's equal to 0, then these are all equal to 0. And so if any AI is non-zero, that forces the value of t, so it can only be 0 at one place, and then the discriminant is just 0. So this is true. And so you can see what the equality case is, that you would need AI bj to equal bi aj for all distinct I and j, you can see. And so this is just equivalent to either the AIs are all 0 or the BIs are all 0, or they are sort of, they're proportional. And this is Koshi-Schwarz. And then one other proof that should be mentioned is that if you, okay, again, assuming the AIs and the BIs are, the AIs are not all 0, the BIs are not all 0, you can, this is homogeneous in the AIs. This is, it's homogeneous in the AIs, and it's, oh, I mean, if someone has a question, you can feel free to ask the question, but if not, you might want to mute yourself. Oh, okay. Okay, it's homogeneous in the AIs, like if you scale them, this scales quadratically, this scales quadratically, and similarly in the BIs. So if the AIs are not all 0 and the BIs are not all 0, which we'll assume, otherwise it would be trivial, let's scale so that the sum of the AIs is 1, the sum of the BIs is 1. Okay, so now we want to prove this now. Which is equivalent to, like, this being between 1 and -1. I want to just write this. And now, like, you can just, again, do term by term. The absolute value of AI plus BI is the geometric mean of AI squared and BI squared. Adding this up over all i's, the AI's sum to 1, the AI squared sum to 1, the BI squared sum to 1, and you get just like so 1 plus 1 over 2, you get 1. And then this big thing is less than or equal to this. This is the triangle inequality, which is not very interesting for real numbers. Like, basically, the absolute value of the sum of some things is at most the sum of their absolute values. This is more interesting for complex numbers, but it's still true for real numbers. And so you can prove it that way.
How does this proof translate to like the by not scaling? Like how to make it isomorphic?
You could, yeah, okay, you could say, like, again, assuming the AIs are not all 0, the BIs are not all 0, you could say, like, if you just take the original numbers, For convenience, I'm going to say let capital A be the sum of the AI's squared, and let capital B be the sum of the BI's squared. So like the scaling thing is just sort of, we would be dividing all the AI's by the square root of A and dividing all the BI's by the square root of B. So if we just proceed without, like, proceed as if we didn't do that, then we would want to take the geometric mean of AI squared over A and BI squared over B as less than or equal to their arithmetic mean. And then this is, because A and B are strictly positive. And then you can add up as before and finish as before. But yeah, that was a good question. And so yeah, you can make it work that way. Also, if you don't want to deal with the absolute values, you could just more directly say like you could just directly write things with like a sum of squares, like AI BI over root AB less than or equal to this, because like the square of AI over root A minus BI over root B, and similarly, you could also get with a negative sign, because by having a plus, and then adding it up, you would just get, what you want. So yeah, that's Koshi Schwarz. Actually, hang on, let me double check that I spelled it correctly. And
also,
so,
is there any way to regularize the vectors proof?
Rigorize, oh, sorry, Schwarz, apparently it should not have a T in it. It's just Schwarz. Rigorize in what way? Like you could fill in the details. Or I mean, which part is not rigorous?
I mean, we like that angle between two vectors in say fourth dimension. That doesn't seem much sense.
I mean, you could, like, I guess you would want to say it's not so like it's not so, I mean, you could prove, like, it's still, what you would want to do is like take a plane through the origin and those two vectors, and then like take the angle in that plane. But like, it's not immediately clear why it would work. You could presumably make it work. Like, the definition ought to still work, but like, it's not so obvious how you would make it work. Yeah, thinking, but maybe you might want to rotate things around, but you would get into some higher dimensional geometry, which is not so easy, but you could presumably make it work. But it is, shall we say, beyond the scope of today's lesson. I was not planning to talk much about higher dimensional geometry much, but yeah, you could presumably make it work, but it's not that obvious. But yeah, that's a good question. Okay. So there's another. Did that help answer your question?
I got that we can regularize this, but not exactly how.
Like, yeah, like you could presumably rigorize it with enough work if you really wanted to, and it might help to look at Wikipedia or some other references, but it's probably kind of hard, and I don't plan to do it today. So yeah, moving along. I guess there's another thing that is nice to talk about, which is the so-called Titus Lemma, which is equivalent to Koshi Schwarz, essentially equivalent to Koshi Schwarz, but it is useful for some problems, which is that if you have real numbers x1 through xn, and positive real numbers y1 through yn, then x1 squared over y1 plus x2 squared over y2, and so on, is greater than or equal to the sum of the x's squared over the sum of the y's. And you can see that this is just like, it's basically the same thing as Koshi-Schwarz, that if you just like bring this factor over here, you could get this by just applying Koshi-Schwarz on like the square roots of the y's. And xi over square root of yi. You could prove it in other ways too. One proof I know of is that you could just, one proof I've seen is like you could just combine two terms, like combining two into one just by direct computation, and it's just direct by induction. Also, you could do that homogenization trick similarly to before. If you like assume that the sum of the yi's is 1, and then and then you assume that the left-hand side is also 1, ignoring all 0 cases, and then you prove it from there. But yeah, so this is like pretty much equivalent, but it can be useful for dealing with some problems if you have, a sum of fractions and you want to make it work somehow. So yeah, and then also I should talk about Holder's inequality.
After we assume LHS is 1 and sum of YIs is 1, how exactly to finish? Like, what's the main idea?
The main idea in what?
Like in this inequality, Titus lemma, after we assume sum of yi is 1 and LHS is 1, what is the main idea in finishing?
In the main idea in proving Titus lemma, or was there something else?
In proving Titus lemma, yeah, finishing the
proof. Yeah, I mean, one way is that this is just Koshi-Schwarz, that like if you just check it, then like you get, this is just
after homogenizing.
After homogenizing. Yes. Let's see. Yes, okay. If the xi's are all 0, it's just trivial. Otherwise, the left-hand side is strictly positive. And so now, like, homogenize the yi's to assume that their sum is 1. Homogenize the xi's to assume that homogenize the yi's to make their sum 1, then homogenize the x's to make this 1, after we've already homogenized the y's. And then you can just say, like, xi is less than or equal to 1/2 and the same for negative xi. And then, if you add this up, you just, like, you get this. less than 1/2 times 1 plus 1. And similarly, the negative is also less than or equal to 1. And so you get that the sum of the xi's is between 1 and negative 1. So it squares at most 1. So you're done. And again, you could also do this with just absolute value signs instead, and then the triangle inequality. So that's how you could prove that.
Okay.
Does that help? Okay. So then I should talk about Holder's inequality. And I told you I was going to also, I guess I have a question for the organizers is it fine if it goes over time? Like if this goes over an hour and a half, is that fine?
It's okay, but
Okay.
it's not preferable in general because I think we start losing people at that point.
Okay. So, okay, yeah. So, okay, Holder's inequality, basically it is a generalization of Koshi-Schwarz to sort of more general exponents, and like you can also do it with more sequences. So, okay, wow, okay, yeah, if you go to the Wikipedia page for Holder's inequality, it's really, okay, I think the Wikipedia page for Holder's inequality, in my opinion, is not very good. It is not very helpful. But yeah, let's talk about Holder's inequality. So for two sequences, basically one way you can think of it is like if you have if you have let's say you have positive reals. One way I've seen it stated is you have positive reals lambda and mu whose reciprocals add to 1. Then the version for two sequences would tell you that if you have, I'll say, positive real numbers, I'll say non-negative real numbers, AI and BI. Then this times this is greater than or equal to this. So you'll notice that if you, for the special case of lambda equals mu equals 2, this is just Koshi-Schwarz, essentially. And you might wonder where do these restrictions come from? Like, why is this natural? Well, it's homogeneous in the AIs, it's homogeneous in the BIs, and if you plug in all the AIs and BIs equal 1, you get n to the 1 over lambda times m to the 1 over mu is greater than or equal to n. And so that's why it's natural to have this sums to 1 condition. And so how do you prove this? Well, we can do some, the usual thing that we've done before, where if you homogenize, you can say, okay, if this is A and this is B, okay, if the AIs are all 0, it's clear. If the B's are all 0, it's clear. Otherwise, the A and the B are strictly positive. And then how does this work? Okay, we want to prove that the sum from I goes to 1 to n. And then, you can prove this by weighted AMGM on these. By, or no, not less than 1. It's less than or equal to this. And then you add it up. You can, convince yourself of the details. I don't want to go, I don't want to take up too much time on this. Someone said something earlier about thinking of something as a basis. I guess this was in relation to Koshi.
Koshi's proof. Like for regularizing it, we can take like A1, I1 plus A2, I2, where like I1, I2 and so on are bases. Then we can use the fact IP dot IQ will be 0 if P is not equal to Q. So that would like regularize it.
Yeah, you can define dot product in multidimensional space. There are definitely ways you can handle multidimensional space. But again, I don't want to get into too much of that. So then you can do this and then, yes?
Yeah, I was saying like if the two vectors are independent, then like their dot product will be 0, no, by definition. So that just works, taking them as bases.
Yeah. Yes, indeed. And then
I'm not sure
okay, yeah,
because that dot product definition with cos and the other thing are not trivially equal.
But actually, another way you could think of it is in terms of sort of the triangle inequality, about like two sides of a triangle being less than or equal to, like, the sum of two sides of a triangle is at least like, the length of its third side. In fact, if you were to apply the triangle inequality on like the AIs and the BIs, you would, like, the distance from 0 to AI, the distance from 0 to B, and then the distance is greater than the distance between them, you would actually get something that is essentially equivalent to Koshi Schwarz, like on doing algebra. I don't want to take up all your time, but you can think about that for later as the Koshi, like that geometric interpretation being related to the triangle inequality, and you can think about that. But I want to have at least some time to talk about some problems at the end, maybe. But yeah, you could sum up and then win. For Holder, you could sum up and win as usual. But it's definitely good to be thinking about the these generalizations and n-dimensional space and advanced stuff. It's definitely good stuff. And then someone was wondering earlier about the relationship of why you can prove power mean inequality with this. Also, I should say you could generalize this in a fairly natural way to if you had more than two sequences. You could prove it by induction by combining them two at a time. If the sum of the reciprocals of a bunch of numbers is 1, but you can think about that later. But like for example, you could have some statement like a1 cubed plus a2 cubed times b1 cubed times b2 cubed times c1 cubed plus c2 cubed is greater than or equal to a1 b1 c1 plus a2 b2 c2 all cubed for non-negative reals a1 b1 c1 a2 b2 c2. And Holder's inequality can be useful in some situations where you have like a bunch of like the product of a bunch of things that are sums or something, or if you have the sum of some product, it can be useful in some various problems. but yeah, to talk about how it's related to power mean, you could say something like, just to give an example of how it worked, of the idea of how something like this should work. I don't want to, dive into all the algebra or something, but if it's something like, if you wanted to prove why, say you wanted to prove like the 7th root of this is greater than or equal to the 5th root of this. And you would presumably do some things differently if you were taking like a negative numbers in the means or something, but I'm just, let's take this as our example. Then what you could do is say something like, how do I want to do this? So we want to take something with x. Let's write something like this: x to the 7, plus y to the 7 plus z to the 7 to the 5/7 power.
Maybe 1 plus 1 plus 1, 2.
Yeah, 1 plus 1 plus 1 to the 2/7 power is greater than or equal to this. And then like you can do some algebra to see that these are equivalent. And then it's just sort of direct by Holder. Like you're just taking lambda is 7/5, and then you plug it in and it's direct by Holder. So that's sort of what's going on, and then you can convince yourself that an argument like that would work in general. But again, I'm omitting some details. Should I go into more detail on this, or should I talk about some, or should I move on?
I mean, you can regress proof, I guess.
Is there a way to like determine what the exponents will be?
Like in I guess for the positive case, you would want to just take like the larger, you would just replace all the 7s by whatever the larger number is, replace the 5s with the larger, and then the 2 is just like whatever 7 minus 5 would be. And then you could, for the case of negative like power means, like if you had like the 5th root of 3 over x to the -5, like you would just take reciprocals of everything to transform it as if you were doing it on positive versions of the x's, and or not positive, but like the reciprocals, and then do that, and then so you could fill in the details, and then if you wanted like a positive here versus that, the geometric mean will lie in between everything. I don't want to cover all the cases. I'm sort of running out of time, so sorry, but let's probably move on to a few problems. But that's sort of the proof in a very vague sense of the word. Okay, so as for problems, so I will actually, this is not the first time I have taught a class on inequalities. And so last summer I taught a class on inequalities for a series of classes called Math Divulged. And I think there was a use, so you can actually, if it's useful, you can find a recording of that on a website, which I'll give you a link to. But there was also a handout I made a while ago that had a lot of problems on it. And so I will put a link here. And so I guess here are some problems What do people want to hear about?
Between which options?
Like anything on this handout, really. Or, yeah.
I think you can just pick the problem which you find the most elegant, or the solution is
Okay.
instructive.
So
1983 problem 6 looks cool.
1983 problem 6.
It's 2.6 on the handout.
Oh, okay. Oh, this is another idea, which is useful. Oh, also, since I'm sort of pressed for time or something, I should also mention the very briefly mention the rearrangement inequality, which basically says, very briefly mention, which is like if you have a list of numbers x and another list of numbers y, and you want to maximize the product of one times another, if you can reorder them, you get the best product when you know, like the sum of the products, you want to order them in the same order. And like, you know, intuitively, it's like, one way I've seen it explained is basically like, suppose you have a box with $100 bills and another box with $10 bills and another box with $1 bills. And someone is like, okay, you can pick 97 bills from one box and 7 bills from another box and 2 from another one. Well, obviously, if you want to maximize your money, you would take 97 hundreds and then 7 tens and then 2 ones. Like, you know, just sorting them in order sort of a thing. This can be useful sometimes, but I will just sort of briefly mention it like that because of time. Okay, so let's see problem 2.6. So, okay, let A, B, and C be the lengths of the sides of a triangle. Prove this. Okay, and so there's an idea here, the so-called Ravi substitution, I think named, I'm not sure who it's named, exactly who it's named after. It might be Rav. There are a couple of people it might be named after, but the so-called Ravi substitution is that when you have the lengths of the sides of a triangle and you want to do things with them, it might be useful to set A equals y plus z, B equals x plus z, C equals x plus y. Basically, because this will encode the condition that they're the lengths of the sides of a triangle. It encodes why like each sum is like A plus B is greater than C, you know, B plus C is greater than A. You can think of this as the lengths from the incircle, like tangents to the incircle. And so these, and equivalently, you could say like x is this. So yeah, okay, so x, y, and z are strictly positive. So then if we plug in, what do we get? We get y plus z squared times x plus z times a minus b being y minus x, and then a cyclic sum of this. All right, cyclic to like sick, to denote that what we're going to do is just sort of cyclically permute to get the other terms, like replace the y's with z's, replace the z's with x's, replace the x's with y's. And we want this to be greater than 0. Now I think we could probably just expand. Let's see. This is probably not super elegant, but let's see. What do you get if you, at this point, but this Ravi substitution can be a useful idea if you have problems about the lengths of the sides of a triangle. What do you get? Well, okay, since we are running low on time and there's no real idea involved in getting the cyclic sum, I'm just going to ask Wolfram alpha. Obviously, do not do this in a real contest, but you know, you all know how to multiply polynomials and add them. So let's just real quick ask Wolfram alpha, what do we get? Y plus z squared times x plus c times y minus x plus x plus z squared times x plus y times z minus y plus x plus y squared times y plus z times x plus z. Okay, expand that. Okay, now Wolfram alpha tells me that the result of doing this computation is that the sum is equal to 2x cubed z plus 2, you get this minus, I'm slightly, editing the way Wolfram alpha would present it, but you get minus 2 times and now this is like very easy to prove why this is greater than or equal to 0, dividing by 2 and then dividing by x, y, z. It's equivalent to just saying, x squared over y plus y squared over z plus z squared over x is greater than or equal to x, y, z, x plus y plus z. And this is immediate by just T2's lemma, because this is, x plus y plus z squared over y plus z plus x. So that proves the problem. And another way you could have written it is just to write, x squared over y greater than or equal to 2x minus y, and then sum it up. There's also another solution where you could apply weighted AMGM to get this x squared yz as a weighted geometric mean of these. I think it involves something like 4/7, 2/7, 1/7, and then summing that up will give you what you want. Because let me explain where that comes from, is that there's sort of this notation, which is useful if you want to do these computations, known as Chinese triangle notation, or by other less polite names, which is basically like if you have a homogeneous 3-variable polynomial, you want to write it in this big triangle. So okay, let's look at it like this. So then it's a useful way of helping to do computations in some problems. So, and then we're going to look at it as like, okay, let's say x at the top, y over here, z over here. So then like the number at this top point will represent the coefficient of x to the 4. And then going down into the left will change an x to a y. Going down into the right will change an x to a z. And so you can sort of see this as a nice graphical representation of this stuff. And so then in this notation, we want to prove an inequality like 2, 2, 2, negative 2, negative 2, negative 2. This is greater than or equal to 0. And so you can sort of see where these numbers come from, in that like you can sort of like, if a point, like since all these points lie inside this triangle, you can sort of get it as a weighted average of these 3 vertices. And so if it's like 4/7 contributed to this point, and so that's another way of doing that. I think maybe if we want to do like one more problem, and also like if people have questions about any of this stuff, since I know I've been like leaving out a lot of details today, you can ask me if you want to write to me. If you have questions about this stuff, you can message me on Discord. I put in the chat what my what my ID is. So you can message me on Discord if you have like further questions, because I know I'm sort of rushing through stuff. But so I guess we've already reached what was officially the end, but maybe if we want to do like one more problem, is there like one more problem people would want to see?
Well, I have
Yes.
a doubt.
Okay. Do I need to, should I just end now, or is there like, is it, or like, like which problem do people want to see if there's still time? Or wait, Pranav, if you can say something, okay, I can hear you.
Yeah. So I was asking, like, in this triangle, I got the coefficients, but what was the relation? I didn't get that.
Like, it sort of relates to this idea of like barycentric coordinates, or like mass points. Like, you can think of like a weighted geometric mean as sort of being like the center of mass. So like, in a sense, like if you put a like, for example, if you put a mass of like 3 kilograms at y to the fourth and 1 kilogram at z to the fourth, then like their center of mass would be 3/4 of the way. It would be here. And indeed, like if you took a weighted geometric mean of like y to the fourth cubed times z to the fourth, fourth root of that, you would get, if they're positive, y cubed z. And so, like, by thinking of these sort of as like centers of mass, sort of barycentric coordinates sort of a thing, like you can get a relation of weighted, like that's where that thing I said about like 4/7, 2/7, 1/7 comes from. It's like you can think of it as like geometric means as a relation of that. But also, like, this is also just a useful shorthand of handling a bunch of coefficients, because it's very useful. You can read some things off, like Amgm is the point between two other points or whatever. You can also have this Schwarz inequality, which is in this problem set about like, which gives you a relation like, one, for at least one special case of it, gives you like this. Is greater than or equal to 0, and stuff like this. But there are some problems that involve doing computations with a triangle like this. But yeah, do people want to see, like, if people want to see one more problem?
Maybe JMO 2011 too.
Okay, JMO 2011 too. Okay. How do you do this? Let's see. Okay, so let's see. So
it is problem 3.12.
Yeah. Okay, let's do this problem then. So okay, you have some. What is the problem? You have positive real numbers a, b, and c satisfying some weird condition, and you want to prove some other condition. Let's see. So okay, a, b, and c are positive real numbers, so that a squared plus b. It is given that a squared plus b squared plus c squared plus a plus b plus c squared is at most 4. Prove ab plus 1 over a plus b squared plus the sum of similar things is which way is it supposed to point? Is greater than or equal to 3. Okay. So let's see. Also, I guess the IMO problem I did earlier, it also asked about the equality. What is the equality case? Sometimes you see problems that will ask about the equality case. If you do, you need to handle it, which I guess I neglected to do. But I guess I will mention it now briefly, which is that like in the solution I mentioned about, wanting to prove this, like to get equality, you would need equality in all of these, and then you would, which would require the x, y, and z to be all equal. Because like to have equality, you would need equality in all those. So then the x would equal y would equal z would equal x, meaning in the original case, a equals b equals c, making that the only equality case. If you were to allow the triangle to be degenerate, as in to have like the three vertices be collinear or something, you could see that there's like an additional equality case if like 2 of x, y, and z are 0, like if 2 of a, b, and c are equal and the third one is 0. But yeah, you can check that yourself, sort of left as exercise or something, like left as exercise if you want to do it. Anyway, back to this problem. So first of all, let's have a look. So like this term, like you have this weird combination of like a quadratic term and a constant term. And so, okay, let's start off by saying, if we don't want this constant term there, we can just replace, we know 1 is greater than or equal to this thing. So let's just replace these ones by this thing. And so let's prove AB plus, like we can see that this whole expression is greater than or equal to this cyclic sum. And so it's sufficient to prove this. How does this, and then let's see, from here, yes. All right. So we don't want to just have to carry this expression around all the time. So if we expand it, we know that a plus b plus c squared, sometimes inequalities involve some amount of algebraic manipulation. So we get 2a plus b plus c squared plus that other stuff. So we can cancel a factor of 2, and we get that this expression is equal to this. Okay. This is just multiplying through by 2, we get this. And now we're actually almost done. Because like the expression we want to prove is this. But now we're almost done because we can just sort of subtract 1 from this term, because 2ab plus a squared plus b squared, that's just a plus b squared. So if we subtract 1 from each of the 3 terms, it's equivalent to proving this. But now what's left? C squared plus AB plus AC plus BC. Well, look, this expression factors C plus A, or I'll write it as A plus C times B plus C. We want to prove this. But this is just clear by Amgm. It's just like this plus, you got shifting the A to B. and you want to prove this, but now like you want it's equivalent to this, and this is just AMGM. Like the geometric mean of these three numbers is just 1. Everything cancels out, and so this is just true, and so you're done. Now, mind you, what I just described is sort of how you could solve the problem, but this is not how you would write the solution up in an Olympiad. You probably could, since I think like everything I did was reversible, but in an Olympiad, it would probably be better to you sort of. I think there's an article on the Art of Problem Solving website about how to write proofs that says something like, think backwards, write forwards. And that's sort of what is going, how you would want to write it up here. You would start by saying, by AMGM, we have this. So we have this. And then you would add in that and say, so it's this, this thing plus that is greater than or equal to 6. So we get, AB, 2AB plus that whole thing is greater than or equal to 6. And then, do the manipulations to show why you get the version with, this over 4, and then say, so we get that, so we're done. When you write up a proof in an Olympiad, you want to be sure to start from what you're given and end up with what you want to prove. Because if you're sort of starting with what you want to prove and ending up with the given, that's a way to, potentially make a mistake. If everything you did is reversible, it's probably fine. Like in this case, we probably could have just gotten away with saying like if we had just drawn if and only if arrows everywhere between like the version with this over 4 and this endpoint, like it would be fine. But you're probably safer not doing that in general. Okay, any questions, any requests for additional problems? I have time to keep staying if people want to see like a couple more problems, or if there are any questions about this.
Can you recommend some handouts or books on inequalities?
Oh, handouts or books on inequalities? I would say, I think on Evan Chen's website, his handouts are probably pretty good. Let's see, what does he have? He has a couple of, there should be, there are a couple of things about inequalities on this page. There's also something about inequalities in this thing he wrote, the so-called Otis excerpts. Oh, and someone in the chat is recommending a book. I don't know exactly which book you're talking about, but I imagine it's perhaps good. But this Otis excerpts talks about some fundamental stuff about inequalities, and also a lot of other neat Olympiad stuff too. So this is some good stuff. Oh yeah, there's a lot of good stuff. Okay, then someone wants to see problem 3.24, Bulgaria TST. Okay, maybe this will be the last one of the day. Okay, prove that if A, B, and C are positive reals, then A, B, and C are positive real. Marker. So A, B, and C are positive reals. I'll give you all take a few minutes. I guess I should have maybe given you a few minutes to think about some other stuff. But yeah, this problem is really not so easy, and so you should I don't want to just jump straight into the solution without giving you some time to think about it first. So really I will take 5-ish minutes to let you all think about this. And like you could probably solve it in theory if you were to just like clear all the denominators, like just multiply by the product of all these, and then just like expand a lot of polynomials. But that seems like it could be very, very unpleasant, like a lot of calculations, which I don't really want to do. You know, so if you want to, you know, maybe if you had Wolfram Alpha, it would not be so bad, but I don't really want to do that. So let's not do that solution. Instead, we can solve it some other way. So you can, so take like 5 minutes approximately to think. Oh, and yeah, if you have to go, that's fine. I imagine a recording of this whole thing will be on YouTube anyway, but yeah, like if you have to go, that's fine, but you know, you can stay if you want. So yeah, take like maybe 5 minutes to think about it. Someone says, why does it feel like a functional inequality? The solution I have in mind is, I'll say now, it involves some clever use of Titus lemma, but I mean, maybe you could find some solution using Jensen or something, but the solution I have in mind is some clever use of Titus lemma. Yeah, okay. So maybe I'll start saying about how you would look at this. So, okay, just as a hint, I'll say, or I guess I can sort of start going into the solution. So as a hint, I'll say that this thing, like you might notice how 3, 4, and 5 are the sides of a right triangle. That is irrelevant. It is not useful that it's this Pythagorean triple. It is useful that they're like 5 is sort of not too big, but so you can notice that there's an equality case when they're all equal. In general, when you're doing things with an inequality, you want whatever you're doing to preserve the equality cases. Evan Chen has written about this in some of his stuff, like more generally, like, but that's a special case. Like whatever we want to do, we want to, preserve the equality case of all the A, B, C are equal. That's maybe more useful to think about when you're doing some inequality with more complicated equality cases. He calls this like the equality principle, but for this, it's still useful to think, okay, that's it. That's an equality case. And also, like, it's important that 5 is sort of not too big, because like if you replaced 5 with like 1,000,000 and replaced 12 analogously with the sum of whatever it is, like if you wanted to prove something like this, in quotation marks, then like this is false. In fact, the inequality would point the other way. So we will use that 5 is not too big. So let's take a look at applying, but that'll tell us what the wrong path to go. That'll sort of tell us about which path to go down, because we don't want to. Oh, someone wants to set A, B, and C to be x squared, y squared, and z. Oh.
Then the numerator like becomes perfect, so and then you can apply T2.
Oh wait, does that just work?
I
Oh wait, hang on.
I didn't take
Hang on, this actually. Oh, okay. I was going to do something more complicated. Wait. How does?
Oh wait.
Oh no.
I did the
Sorry,
inequality sign.
that does not. You can't. I don't think that works. The
I took the
difficulty.
inequality sign wrong in the T2.
I think so. Okay. Yeah, because like, yeah, you could use this to. If you wanted to use T2 in this way, you would get something like this sum of fractions is greater than or equal to like root AB plus root BC plus root CA squared over 12A plus B plus C. But that doesn't tell us what it's less than or equal to. So yeah, it's a good try, but not exactly what we want. So let's see. And so if we were to make a first try at applying this to do something like, AB equal over like A plus A plus A plus B plus B plus B plus B plus C plus C plus C plus C plus C, you could probably eliminate having to write it multiple times if you took appropriate weights. And I'll look at this as like 1 over 144 times, a bunch of 1s squared. You could say, okay, this is less than or equal to 1 over 144 times, AB, 3 of these, etc. But like eventually, if you try to apply T2 in this just naive way, like you would eventually end up with some term of this form. And again, as we said before, like you can actually prove that this is greater than or equal to A plus B plus C quite easily. Just apply AMGM on terms 2 at a time.
How do you get that inequality exactly?
Oh, you can just say like AB over C plus CA over B 1/2 of this is greater than or equal to their geometric mean, which is just A. And you get similar things for the other two, and you add it up, and you get that. So yeah. So just applying T2 like this is not the right way to do it, to solve the original problem. So let's if we play around with some stuff. What if we combine the C with some other stuff? So if the coefficient, we might wish that we could.
How does T2 imply the inequality?
Oh no. For this inequality, it was just that Amgm 3 times that
the above inequality.
Oh, this? Oh, yeah, I'm just sort of. Oh yeah, this sort of AB this 1/144 times AB. This is just sort of a useless extra factor. The point is just like the sum of 12 ones over the sum of all that is less than or equal to 1/A, etc.
Okay, got it.
Plus 1/A plus, yeah. And also you could think of this as just the inequality between the arithmetic mean and the harmonic mean is another way, which is sort of a special case of, it's a special case of the power mean inequality. It's another way of looking at it. But yeah, either way, like this is not strong enough. So what if we combined C with other stuff? Well, maybe we wish we could make a bunch of terms that are A plus B plus C. But since the coefficient of C is bigger than the A and B coefficients, like we're going to run out of terms. We couldn't just make enough A plus B plus C terms to apply T2 on. Okay, what if we combine C with only A or B? And if you keep thinking about stuff like this, eventually you hit upon some neat thing you can do, which is that we're going to split this up as follows. AB over this equals AB over 1/2 times A plus 3/2 times B plus 5/2 times A plus C plus 5/2 times B plus C. It will be important that these coefficients of A plus C and B plus C are the same as each other. Okay, so now if we, let's see. So we want to apply T2's lemma to this. And so again, if when you apply Koshi-Schwarz, if you want to preserve some equality cases, you want things to be proportional. So, if A and B and C were all 1, you would get like 1/2, 3/2, 5, 5. So let's think about applying T2 on that. And then this is, again, 144. Wait, is that clearly? Okay, I think it's pretty visible. And so, okay, a factor of that to cancel it out. So this expression is less than or equal to 1/144 AB, just that factor, times 1/2 squared over 1/2 A plus 3/2 squared over 3/2 B plus 5 squared over 5/2 A plus C plus 5 squared over 5/2 B plus C. Okay. And if we take a look at what we get, what do we get? We get the inside of this expression is 1/2A plus 3/2B. Oh no, sorry, this is not squared. Plus 10/A plus C plus 10/B plus C. Okay. And now we get, this is, okay, B over 288 plus A over 96 plus 5/72 times AB over A plus C plus AB over B plus C. Now we will see the reason why we cared about having the same coefficient of 5/2 here and here. Because when you add this up cyclically, we want this A be like a cyclic sum, as the same as before. Like this AB over A plus C, we're going to add it when we cyclically sum this. On the next term, there's going to be a BC over C plus A, and with the same coefficient as before. We're going to take this. Here, I'll rewrite it over here. We want to take this expression and cyclically sum over A, B, and C. Because when we, on the next term, there will be a, like a BC over A plus C. Like the B goes to C, C goes to A. And then with the same coefficient. And look what we have. AB over A plus C plus BC over A plus C. That's just B. Meaning all the fractions just cancel out. When we add it cyclically, we get that the sum of the original left-hand side of the inequality is less than or equal to A plus B plus C over 288 plus A plus B plus C over 96 plus 5/72. We get a B and we'll get a C and we'll get an A from just adding the stuff up. And when you add this up, you get exactly A plus B plus C over 12 as desired, the end. So that completes the proof. And if you're wondering where you get these things, if you played around with Titus lemma in the right way, and if you didn't want to take these magical coefficients, you could just if you just multiplied the denominator, you could have just scaled by a constant factor and just written out if you multiplied by 4, you could have just written out something like A plus A plus B plus B plus B plus B plus B plus B. You could have just written out an A plus A plus B plus B, 3 of them, plus A plus C times 10, and similarly for B plus C, 10 times. If you just wanted a more direct way of applying, seeing where these coefficients come from, 1, 3, 10, 10, and if you wanted motivation for where these all came from, it's okay, if you didn't try to make the coefficients of A plus C and B plus C equal, this last step wouldn't work out. So if you maybe you could have tried some different attempt and realized it failed at the last step and then adjusted it to make it work out. And then it's just the coefficients of A plus C and B plus C are equal and they use up all the C's, and then we just use up the leftover A's and B's.
But what was the motivation of viewing A plus C and B plus C as variables?
That's a good question. That you have to combine something with the C, and maybe, maybe earlier if you had wanted to try A plus B plus C, but you realize that won't work out because the 5 is too big. And then maybe if you think, oh, maybe I'll use A plus C or B plus C. And then if you just eventually play around, and if you eventually realize that you'll get some nice cancellation, eventually you think of this. But this is not an easy problem, I would say. It's pretty, this is maybe somewhat tricky, maybe. So yeah. But if if you realize that this will come out of it, eventually you would want to come up with it. That's sort of where all the motivation comes from. But yeah, so that's this problem. And so I guess I'll stop there. Oh, someone said, is it helpful to have a strong background in calculus for solving Olympiad inequality problems? So I would say it can help sometimes, and it can especially help to be familiar with some concepts like concavity or something. But like some problems maybe we'll use something like that, but some problems, like a lot of the time, maybe calculus. Some problems maybe it would help to know concepts from calculus, and sometimes it can help to do some calculus. Like if you want to apply Jensen, you might need to take the second derivative of something. But it's not the most important thing. So it can help, but it is not like maximally important. But like it can definitely help if you're just trying to execute some ugly bash solutions. Like especially there's this technique called Lagrange multipliers, which you can see about on Evan's website, but it's basically like you bash inequalities with calculus until they die. But it has a reputation for being ugly, but it could help, but like and also like calculus is just really good to know in general, like for life and for like furthering your education in math, or if you want to learn physics or that sort of thing. But like, so there are definitely other reasons to know calculus besides Olympiad inequalities, but don't feel like you have to know calculus. Like, the idea is that you generally, supposedly you can solve everything without calculus or something. But they definitely have relaxed some. Maybe sometimes you need to know some basic concepts with concavity or whatever. I have a particular example in mind, but I don't want to spoil too much. But don't worry too much about calculus. But there are definitely like other reasons to learn it. Someone asked like, why would you learn Lagrange multipliers? It's pretty ugly. I don't really know exactly. I have maybe some vague ideas about how it works, but I'm not exactly an expert in that myself. But like, it can be a good thing to know. Anyway, but yeah, I guess I'll stop there for today. So thank you all for being a very good audience, and thank you especially to the people who still stuck with me. Thank you all for coming. So
Thanks
for
a lot.
taking the class.
Yeah, thanks a lot for conducting this. I think it was quite helpful to all, and it was a great class.
Thanks for
thank you.
conducting the class.
Thank you all for coming, for being great students. Thank you.